Hello everyone, my name is Santosh and I am a student of Chemistry Honors first year, and it is an audio video recording on periodic properties. Here I start. Periodic properties. The concept of periodicity has acquired the key position in the study of inorganic chemistry. No other generalization competes the periodic table of the elements in its ability to simplify, systemize and rationalize known chemical facts. At present, about 118 elements are known which have numerous properties and form millions of the compounds. The periodic classification of elements has extremely simplified their study. Many different forms of the periodic table have been proposed depending upon the purpose for which the table is used. However, the most commonly used form is known as the long form of the periodic table. Let us briefly recapitulate the development of periodic table. Its salient features is already studied in earlier classes and important periodic properties and their applications. Development of the periodic table. Since the beginning of the 19th century, scientists have been trying to find a basis of grouping elements having similar properties. Though several scientists, namely Lavoisier, Daubernier, Newlands, Mayer, and Mendeleev, attempted to find certain regularities among elements, the first important attempt to divide the elements on the basis of their physical and the chemical properties was made by a German chemist Lothar Meyer and a Russian chemist Mendeleev. They observed that when the elements are arranged in the order of increasing atomic weights, the elements with the similar properties recur at regular intervals. Mendeleev gave a law known as the periodic law. The law states that the physical and the chemical properties of elements are periodic function of their atomic weights. The Mendeleev's classification gave him so much confidence that he boldly left certain spaces or gaps for undiscovered elements. By considering the properties of the adjacent elements in his table, he predicted the properties of these undiscovered elements. Later on, when these elements were discovered, their properties were found to be exactly similar to those predicted by Mendeleev. For example, gallium and germanium were not discovered at that time when Mendeleev formulated his periodic table. He not only predicted the existence of these elements, but he also estimated their properties. He named these elements as Ika aluminium and Ika silicon because he believed that these would be similar to aluminium and silicon respectively. When chemists discovered these elements, Mendeleev's prediction of their properties proved to be remarkable correct. Modern periodic law. In 1912, Moseley shows that the physical and the chemical properties of the atoms of the elements are determined by their atomic numbers and not by their atomic weights. This acceptance of atomic number as the important characteristic of an atom led to the modern periodic law, which may be stated as the physical and the chemical properties of the elements are periodic function of their atomic numbers. Consequently, when the elements are arranged in the order of their increasing atomic number, it is observed that the elements of similar properties recur at regular intervals or periodically. As a result of this, the elements fall in certain groups and lead to an arrangement called the periodic table. With the modern periodic law as the guiding principle, many new forms of the periodic table have been proposed. However, the general plan of the table has remained the same as proposed by Mendeleev. Of these, the most commonly used form is known as long form of periodic table. The long form of periodic table and the position of elements in the periodic table. The most widely used periodic table these days is the long form of the periodic table. This is constructed on the basis of repeating electronic configuration of the atoms when they are arranged in the order of increasing atomic numbers. Long form of periodic table is given on the next page in the book. Structural features of the long form of the periodic table. The long form of periodic table consists of horizontal rows known as periods and vertical columns known as groups. They are discussed as periods. A horizontal row in the periodic table is known as period. In terms of electronic structure of the atom, a period constitutes a series of elements whose atoms have the same number of electron shell, principal quantum number, that is n. There are 7 periods and each period starts with a different principal quantum number. Now groups. A vertical column in the periodic table is known as a group. In terms of electronic structure of the atom, a group constitutes a series of elements whose atoms have the same outermost electronic configurations but they have different number of total electrons. There are 18 groups in the long form of the periodic table. According to the new recommendations of the International Union of Pure and Applied Chemistry, that is known as IUPAC, the groups are numbered from 1 to 18. Previously, these were numbered only from 1 to 8 as A and B groups. Both the systems of numbering the groups are given in the periodic table. However, the old convention is still used in many books. Discovery and nomenclature of elements with atomic number more than 100. The first scientific attempt to prepare the elements beyond uranium were made by Enrico Fermi and co-workers in 1934. They irradiated uranium with slow neutrons and found several radioactive products which were found to be due to the new elements. The continued effort of scientists led to many new elements, and these were called transuranium elements. Today, we have elements up to 118. These elements were earlier named traditionally by its discoverer or discoverers. However, in recent years, disputes regarding the original discoveries of the some elements of atomic number 104 and above have arisen. After several years of discussion by the Commission in Nomenclature of Inorganic Chemistry CNIC and comments of chemists around the world, IUPAC in 1997 gave the approved official names for the elements with atomic number 104 to 109. However, the names of elements with atomic number 110 and above have yet to be officially announced, and they may be announced before. To solve the problem, IUPAC recommended a nomenclature to be allowed for naming these new elements until their names are officially recognized. This nomenclature is based on the Latin words for their numbers. For example, nil for 0, un for 1, bi for 2, tri for 3, quad for 4, pent for 5, hex for 6, sept for 7, oct for 8, and in for 9. The names are derived by combining together the roots in the order of digits which make up the atomic number, and em is added to the end. For example, the atomic number 104, the name may be written as 1 means un, 0 means nil, 4 means quad, plus ium, em means totally said as unnil quadium. Classification of elements into S, P, D and F blocks. The long form of periodic table can be conventionally divided into 4 main blocks. In this division, the elements which involve the filling of particular orbitals, that are S, P, D or F, are grouped together. S block elements. The elements in which the last electron enters the s orbital of their outermost energy level are called S block elements. It consists of elements of groups 1 and 2 having the ground state electronic configuration of outermost shell as ns1 and ns2 respectively, where n stands for the outermost energy shell. The elements corresponding to ns1 configuration are called alkali metals, while those corresponding to ns2 configuration are known as alkaline earth metals. Thus, the general electronic configuration of S block elements may be expressed as Ns1 2. P block elements. The elements in which the last electron enters the p orbital of their outermost energy level are called p block elements. The elements of group 3a, or we can say group 13 to 8a, we can say group 18, involving addition of 1, 2, 3, 4, 5 and 6 respectively in p orbitals and s orbitals are already filled in their atoms constitute p block. The general electronic configuration for the atoms of this block is may be written as ns2 np126. D block elements. The elements in which the last electron enters the d orbitals of their last but one energy level constitute d block elements. This block consists of elements lying between S and P block starting from 4th period and onwards. They constitute group 3b to 8b and 1b and 2b. In the periodic table, in these elements, the outermost shell contains 1 or 2 electrons in their s orbitals, but the last electron enters the last but in 1d subshell, that is n-1d. The general electronic configuration for the atoms of the d block may be written as n-1 d1 or to 10 ns1 or 2. Thus, it is the d orbital which is progressively being filled in the elements of this block. These elements are called transition elements. The d block comprises 3 complete rows of 10 elements and 1 incomplete row. These rows are called first, second and third transition series, which involve the filling of 3d, 4d and 5d orbitals respectively. These series are also called transition series. First transition series from scandium to zinc. Second transition series yttrium to cadmium. Third transition series lanthanum to mercury. F block elements. The elements in which the last electron enters the f orbitals of their atoms are called f block elements. In these elements, the last electron is added to the third to the outermost energy level, that is n-2f. These consist of 2 series of elements placed at the bottom of the periodic table. The first series follows lanthanum and the elements present in this series are known as lanthanides. They are also called rare earth metals elements. The second series follows actinium and the elements present are known as actinoids. They are of radioactive nature. The general electronic configuration of F block elements may be written as n-2 F1 to 14 n-1 D01 ns2. For example, for lanthanoids, the general electron configuration is 4f1 to 14 5d0 to 1 6s2, while for actinoids it is 5f1 to 14 6d0 to 1 7s2. The elements included in these 2 series are called inner transition elements because they form transition series within the transition elements of D blocks. Cause of periodicity. The recurrence of similar properties of the elements after certain regular intervals when they are arranged in the order of increasing atomic numbers is called periodicity. The classification of the elements in certain families was based upon the observed similarities in the physical and the chemical properties. But why do certain elements exhibit similar properties, and why do similar properties recur at the regular intervals of the atomic numbers? Were some important questions yet to be answered. We know that an atom consists of nucleus surrounded by electrons. In ordinary chemical reactions, the nuclei of the atoms do not undergo any change, and therefore it is the distribution of the electrons in the various shells of their atoms that determine the physical and the chemical properties of the elements. Further, it has been also found that the properties of atoms do not depend so much on the arrangement of electrons in the inner shells. Thus, it must primarily be the arrangement of electrons in the outermost shell, known as valence shell, that determines the properties of the atoms. For example, electronic configuration of the atoms of alkali metals shows that they all have one electron in the s orbital of the outermost valence shell, preceded by the noble gases configuration, that is ns2 and np6, but for lithium it is ns2. The general electronic configuration of these may be written as noble gases in ns1, where n stands for the principal quantum number. Thus, the cause of periodicity of the properties of elements is the repetition of similar electronic configuration of their atoms in the outermost energy shell or the valence shell after certain regular intervals. Periodic properties. Now, periodic properties are stated as: there are many physical and chemical properties of the elements which show periodic variation with the atomic number. Some of these properties, such as valency, atomic size, ionization energy, and electron affinity, are directly related to the electronic configuration of the atom, while some properties, such as melting point density, are indirectly related to the electronic configuration. Atomic radii. This is very important property because many physical and chemical properties are related to atomic radii. Generally, the term atomic radius means the distance from the center of the nucleus to the outermost shell of the electron. If the atom is assumed to be spherical, it is the radius of the sphere. However, the absolute size of an atom is difficult to be defined because of the following reasons. According to the probability pictures of electron, an atom does not have well-defined boundaries. The probability of finding the electron is never zero, even at large distances from the nucleus. The second one is, it is not possible to isolate an atom and measure its radius. The probability distribution of an atom is also affected by the presence of the other atoms in its neighborhood. Therefore, the size of atom may change in going from one set of environment to the another. Thus, we can only arbitrarily define atomic radius as the effective size, which means the distance of closest approach of an atom to another atom in a given bonding situation. In other words, the atomic radius corresponds to the limit of approach of another atom in a particular substance. Therefore, the atomic radii may be called as covalent radius, van der Waals radius, ionic radius, or crystal radius, depending upon the types of bonding. Here, covalent bond or covalent radius. The radius of an atom is calculated by measuring the distance between the centers of two atoms, that is internuclear distance, in molecules with the help of X-ray diffraction or spectral studies. In the case of homonuclear diatomic molecule, the atomic radius is defined as 1/2 of the distance between the centers of nuclei of two similar atoms bonded together in a molecule. The radius is also called covalent radius because the atoms in a homonuclear diatomic molecule are held together by covalent bonds. For example, the internuclear distance between the two atoms in hydrogen molecule is 0.74 angstrom. Atomic radius of hydrogen will be 0.74 upon 2 angstrom, that is 0.37 angstrom. Similarly, the atomic radii of fluorine, chlorine and bromine are 0.64 angstrom, 0.99 angstrom and 1.14 angstrom respectively, because the internuclear distances in F2Cl2 and Br2 are 1.28 angstrom, 1.98 angstrom and 2.28 angstrom respectively. In the case of heteronuclear diatomic molecules containing different atoms, it has been observed that when the covalent radii of different atoms joined by single covalent bond are added, the resulting value agrees fairly well with the experimental determined internuclear distance of the molecule. For example, the internuclear distance in HCl molecule can be calculated by adding the covalent radii of hydrogen and chlorine. R of HCl is equals to R of H plus R of Cl, that is 0.37 plus 0.99, that is equals to 1.36 angstrom. Metallic or crystal radius. This gives the size of atoms in case of metallic elements. In case of metals, a large number of atoms are closely packed and are held together by means of metallic bonds. The close packing of the metal atoms is known as crystal lattice or metal lattice. And this packing is different in different metals. The metallic radius may be defined as 1/2 of the distance between the nuclei of two adjacent atoms of a metal in a metallic lattice. For example, the internuclear distance between the nearest neighboring atoms in a metallic crystal is determined by X-ray diffraction. This is divided by 2 to calculate the metallic radius, as R metallic is equals to internuclear distance between two adjacent atoms in metallic lattice divided by 2. For example, the metallic radius of sodium is 1.86 angstrom. The metallic radii are larger than the corresponding single bond covalent radii. For example, the covalent radius of sodium is 1.54 angstrom, while its metallic radius is 1.86 angstrom. This is because metallic bond is weaker than the covalent bond, and therefore the metal atoms in metallic lattice are not drawn close to each other as in a covalent bond. Third one is van der Waals radius. Van der Waals radius is defined as 1/2 of the internuclear distance between the adjacent atoms belonging to two nearest neighboring molecules of the same substance in the solid state. It has been observed that there are some weak forces of attraction between the neutral atoms of noble gas atoms and nonpolar molecules of various substances. These are known as van der Waals forces, and due to these forces, the noble gas atoms and nonpolar molecules are held together, particularly in the solid state. Thus, the van der Waals radius corresponds to the closest approach of two atoms of noble gases or non-polar molecules of other substances which otherwise do not form bonds. The measurement of van der Waals radius for chlorine is shown. R van der Waals is equal to internuclear distance between two non-bonded nearest neighboring atoms divided by 2. Intermolecular distances between two chlorine atoms of nearest neighboring molecule is equal to 3.6 angstrom. So the van der Waals radius of chlorine will be 3.6 upon 2, that is 1.80 angstrom. The van der Waals radii of some atoms are given in the table. As evident from this table, the van der Waals radii are larger than the covalent radii. This is obvious because in the formation of covalent bond, the atoms come close to each other due to the overlapping of orbitals. On the other hand, van der Waals forces existing between atoms or molecules are weak and the atoms are at larger distances. Therefore, the internuclear distance in case of atoms held by van der Waals forces is more than that between covalently bonded atoms. Consequently, van der Waals radii are larger than covalent radii. Periodic trends in size. Let us discuss the periodic trends in a group and a period. Variation of atomic radii in a period. In general, the atomic radii decrease as we move from left to right in a period in the periodic table. For example, in the second period, the atomic radii decrease from lithium to fluorine through beryllium, boron, carbon, nitrogen, and oxygen. This could be explained on the basis of increasing nuclear charge along a period. With the increase in atomic number from lithium to fluorine, the magnitude of nuclear charge increases while the corresponding addition of electron takes place in the same principal shell. Since the electrons in the same shell do not screen each other from the nucleus, the increase in nuclear charge is not neutralized by the extra valence electron. As a result, electrons are pulled closer to the nucleus by increased effective nuclear charge and thereby cause a decrease in the size of atom. In this way, the atomic size goes on decreasing across the period. Now, there is a note which explains as the variation in atomic radii in a period can easily be explained on the basis of effective nuclear charge instead of nuclear charge. Effective nuclear charge is equals to the actual charge minus screening constant. The effective nuclear charge increases regularly in a period. Therefore, there is a regular decrease in the radii of atoms from left to right. Variation of atomic radii in a group. The atomic radii of elements increase from top to bottom in a group, and this could be explained as on moving down a group, the nuclear charge is increasing with increase in the atomic number, and we expect that the size of the atom should decrease. However, while going from one atom to another, there is an increase in the principal quantum number. Although the number of electrons in the outermost shell remains the same, the effect of increase in the size of electron cloud is more pronounced than the effect of increased nuclear charge. Consequently, the distance of the outermost electron from the nucleus gradually increases down a group. In other words, the size of atom goes on increasing as we move down the group. Ionic and crystal radii. The ionic radii correspond to the radii of ions in ionic crystals. The ions are formed as a result of addition or removal of electrons from the outermost shell of atoms. The ions formed by the loss of electrons acquire positive charge and are called cations, while the ions formed by the gain of electrons acquire negative charge and are called anions. Ionic radius may be defined as effective distance from the nucleus of the ion up to which it has an influence in the ionic bond. Measurement of ionic radius. The X-ray studies give the distance between the nuclei of adjacent positive and negative ions in the crystal. If the ions are regarded as spheres, the internuclear distances may be taken equal to the sum of the radius of the cation and the radius of anion. For example, the internuclear distance of NaCl is 2.76 angstrom, which corresponds to the sum of ionic radii of Na positive and Cl negative ions. But the problem of assigning different values to constituting ions is not simple. Unless the radius of any one ion is known, we cannot calculate the radius of other ion. Several methods have been proposed to calculate the ionic radii of ions. Out of the various methods, Pauling method is most widely accepted. Pauling's method for calculation of ionic radii. This method is based on the calculation of ionic radii from the observed internuclear distances from a set of ionic compounds which have the cation and anion isoelectronic. Their cations and anions have the same number of electrons. He selected four ionic compounds that are NaF, KCl, RBBr, and CSI. In each salt, the cation and anion are isoelectronic. For example, in NaF, both Na positive and F negative have 10 electrons. Pauling suggested that for the isoelectronic ions, the radius of an ion is inversely proportional to the nuclear charge of Z effective of the ion, that is, R is inversely proportional to the Z effective. Z effective is known as equals to Z minus S, where Z is the nuclear charge and S is the screening constant. So R is equals to C upon Z minus S, where C is the proportionality constant and it is same for two isoelectronic ions. The effective nuclear charge Z effective can be calculated by subtracting a screening constant from the actual nuclear charge. The value of screening constant is calculated from Slater's law. Let us consider an example of sodium fluoride. The internuclear distance in NaF has been found to be 2.31 angstrom, so that Rna positive plus Rf negative is equals to 2.31 angstrom. Both Na positive and F negative ions are isoelectronic and have the same value of screening constant. Now, size of cation and the anion. Size of cation. In general, the size of a cation is smaller than a neutral atom, and this is due to the fact that the no removal of electrons from an atom, the magnitude of nuclear charge remains same while the number of electrons will decrease. As a result, the nuclear charge now acts on lesser number of electrons. In other words, the effective nuclear charge per electron increases and the electrons are more strongly attracted and are pulled towards the nucleus. This causes a decrease in the size of an atom. For example, the atomic radius of sodium is 1.54 angstrom, but the ionic radius of Na positive is equals to 0.95 angstrom. Size of the cation and the anion. In general, the negative ion or anion is always larger than the corresponding atom. The negative ion is formed by the gain of one or more electrons in the neutral atom, and the number of electrons increases while the magnitude of nuclear charge remains the same. As a result, the same nuclear charge acts on large number of electrons than are present in the neutral atom. In other words, the effective nuclear charge per electron is reduced and the electron cloud is held less tightly by the nucleus. This causes an increase in the size and thus anions are larger in size than the corresponding atoms. For example, the atomic radius of chlorine is 0.99 angstrom, while the ionic radii of chlorine negative, Cl negative, is 1.81 angstrom. Periodic trends in ionic radii. Variation of ionic radii in a period. For an isoelectronic series, ions having same number of electrons, the ionic radius decreases as the nuclear charge increases. And this could be explained as in an isoelectronic series there is an increase in nuclear charge and therefore the attraction for the same number of electrons increase. As a result, the electrons are pulled more and more strongly and thus ionic radius will decrease. Variation of ionic radii in a group. As we go down a group, the ionic radii increases with increase in the atomic number, like atomic radius. And this could be explained as this is mainly due to the increase in the principal quantum levels. The effect of increase in the principal quantum level is more pronounced than the effect of increased nuclear charge. Ionization energy. The ionization energy gives a measure of the ease with which an atom can lose an electron and change into a cation. Ionization energy of an element is defined as the amount of energy required to remove the most loosely bound electron from an isolated gaseous atom. Ionization energy is also called as ionization potential because it is measured as the amount of potential needed to remove the most loosely held electron from the gaseous atom. The experimental values of ionization energies are determined either by spectroscopic methods or by passing an electric current of gradually increasing intensity through the vapors of the element in a discharge tube. It is expressed in terms of either kilocalorie per mole or kilojoule per mole or electron volt per atom. Thus, the ionization energy gives the ease with which electron can be removed from an atom. Evidently, the smaller the value of ionization energy, the easier it is to remove the electron from the atom. Factors on which ionization energy depends. The magnitude of ionization energy for an atom depends upon the following factors. First is the size of atom. The ionization energy depends upon the distance between the electron and the nucleus, that is size of atom. The attractive force between the electron and the nucleus is inversely proportional to the distance between them. Consequently, as the size of the atom increases, the outermost electrons are less tightly held by the nucleus. As a result, it becomes easier to remove the electron and therefore ionization energy decreases with the increase in the atomic size. Charge on the nucleus. The attractive force between the nucleus and the electrons increases with increase in the nuclear charge. This is because the force of attraction is directly proportional to the product of charges on the nucleus and that on the electrons. Therefore, with the increase in nuclear charge, it becomes more difficult to remove an electron and ionization energy will increase. The third one is the screening effect of the inner electron. In multi-electron atoms, the outermost electrons are shielded or screened from the nucleus by the inner electrons, and this is known as the shielding effect or the screening effect. As a result of this, the outermost electron does not feel the full charge of the nucleus. The actual charge felt by an electron is termed as the effective nuclear charge, and the effective nuclear charge is equal to the total nuclear charge minus the screening constant, where screening constant takes into account the screening effect of the inner electrons. If the number of electrons in the inner shell is large, the screening effect will be large. As a result, the nucleus electron force will be less. Consequently, ionization energy will decrease. Thus, if other factors do not change, an increase in the number of electrons tends to decrease the ionization energy. The fourth one is the penetration effect of electrons. It is well known that in case of multi-electron atoms, the electrons in the s orbital have the maximum probability of being found near the nucleus, and this probability goes on decreasing in case of p, d and f orbitals. In other words, s electrons are more penetrating towards the nucleus than the p electrons, and the penetration power decreases in a given shell in order s, p, d, f. Now, If the penetration of the electron is more, it will be closer to the nucleus and will be held firmly. Consequently, the ionization energy will be high. This means that ionization energy increases with the increase in the penetration power of the electrons. Thus, for the same shell, the required ionization energy would be more to remove an s electron than to remove a p electron, which in turn will be more than that for the removal of a d electron, and so on. The fifth one is the electronic configuration. The ionization energy also depends upon the electronic configuration of the atom. It has been observed that certain electronic configurations are more stable than the others. For example, half-filled and completely filled shells have extra stability. Boy. Half-filled and completely filled shells have extra stability associated with them. Consequently, it is difficult to remove electron from these stable configuration and ionization energy is high. This may be illustrated by some examples. The noble gases have the most stable configuration in each period and have highest ionization energy. The elements like beryllium and magnesium have completely filled orbitals and their ionization energies are large. The elements like nitrogen and phosphorus have the configuration in which the orbitals of same subshell are exactly half filled and are also stable. Hence, they need large energy to remove the electron. Their ionization energies are high. Thus, the more stable the electronic configuration, the greater is the ionization energy. Variation along a period. In general, the ionization energy increases with increasing atomic number in a period. This is quite clear from the values of ionization energy of the second row elements. The general increase along a period can be explained on the basis of atomic size and nuclear charge. We know that on moving across a period from left to right, the nuclear charge increases and the atomic size decreases along a period, though energy levels remains the same. As a consequence of increased nuclear charge and simultaneous decrease in the atomic size, the valence electrons are more and more tightly held by the nucleus. Therefore, more and more energy is needed to remove the electron, and hence ionization energy keeps on decreasing. However, some irregularities in the general trend have been noticed. These are due to the half-filled and completely filled electronic configuration, which have extra stability. To illustrate this, let us consider the variation of ionization energy in the second period going from one element to the another. Lithium to beryllium. On moving from lithium to beryllium, there is an increase in the ionization energy, and this is due to the increased nuclear charge and smaller atomic size. Beryllium to boron. Although the nuclear charge of boron is more than beryllium, yet there is a slight decrease in the ionization energy from beryllium to boron, and this is due to the fact that in boron the last electron goes to 2p orbital, which is at slightly higher energy than 2s, and is easy to be removed. And the second reason is the electronic configuration of boron is less stable than that of beryllium, which has completely filled orbitals. As a result, the 2p electron of boron is not tightly held by the nucleus as 2s electron of beryllium, and hence ionization energy of boron is less than that of beryllium. Boron to carbon to nitrogen. As we move from boron to carbon to nitrogen, the ionization energy keeps on increasing due to increasing nuclear charge and decreasing atomic size. Nitrogen to oxygen. Oxygen, the element next to the nitrogen, has slightly smaller ionization energy as compared to that of nitrogen. It is due to the fact that the electronic configuration of nitrogen atom, in which each 2p orbital is half filled, is more stable than that of oxygen. Therefore, ionization energy of nitrogen is more than that of oxygen. Oxygen to fluorine to neon. The ionization energy increases from oxygen to fluorine into neon because of the increased nuclear charge and decrease in the size. Neon, the noble gas, has the maximum ionization energy in the period due to the stable electronic configuration. Similar variation in ionization energy of the elements of third period have also been observed. Now, variations down a group. Within a group, there is a gradual decrease in the ionization energy on moving from top to bottom. And this is clear from the ionization energy values of the elements of first groups. This decrease in ionization energy down a group can be explained in terms of net effect of the following factors. Going from top to bottom in a group, the nuclear charge increases. There is a gradual increase in the atomic size due to an additional main shell. There is an increase in shielding effect on the outermost electron due to an increase in the number of inner electrons. The effect of increase in the atomic size and the shielding effect is much more than the effect of increase in the nuclear charge. As a result, the electron becomes less and less firmly held to the nucleus as we move down the group. Hence, there is a gradual decrease in the ionization energies in a group. Successive ionization energy. The atom may not only lose one electron but more than one electron also. Therefore, it is essential to specify the definition of ionization energy for each electron which is to be removed. The energy required to remove subsequent electron from the atom in the gaseous state are known as successive ionization energy. The term first, second, third ionization energy refers to the removal of the first, second, third electrons respectively. As can be seen, the second ionization energies are very much higher than the first ionization energies. This is mainly due to the fact that after the removal of the first electron, the atom changes into monovalent positive ion. In the ion, the number of electrons decreases but the nuclear charge remains the same. As a result of this, the remaining electrons are held more tightly by the nucleus and it becomes difficult to remove the second electron. Hence, the value of second ionization energy, that is IE2, is greater than that of the first ionization energy, that is IE1. In the same way, the removal of the second electron will result in the formation of dipositive ion and attraction between the nucleus and remaining electrons increase further. This results in the higher value of the third ionization energy than the second ionization energy. The successive ionization energy of the first 14 elements are shown. The ionization energy is to the right of the stepwise lines correspond to the removal of the electrons from filled configuration of the atoms. As is clear from the table, for each atom there is a large increase in the energy after all the outermost electrons have been removed. For example, in case of sodium, the first ionization energy corresponding to removal of valence electron is 496 kJ per mole, but the second ionization energy corresponding to removal of electron from filled electronic configuration is 4564 kJ per mole, almost 10 times. Similarly, for magnesium, the first ionization energy is 737 kJ per mole and the second is 1447 kJ per mole. Therefore, ionization energy becomes very high. Now, electron affinity. Just as energy is required to remove an electron from an atom, energy is released also when an electron is added to a neutral atom, and this is called the electron affinity. Thus, the amount of energy released when an electron is added to an isolated gaseous atom is known as the electron affinity. As the definition implies, the magnitude of the electron affinity measures the ability of an atom to hold an additional electron. If an atom has more tendency to accept an electron, large energy will be released. Consequently, electron affinity will be high. On the other hand, if an atom has less tendency to hold the electron, small amount of energy will be released, leading to a small value of electron affinity. Electron affinities can be positive or negative. When energy is released during the addition of an electron to an atom, the electron affinity is taken as positive. Electron affinities are expressed in kilojoule per mole. Factors on which electron affinity depends. There are many factors which govern the electron affinity, but the following are some important factors on which it mostly depends. Nuclear charge. The electron affinity increases as the nuclear charge increases. This is due to the greater attraction for the incoming electron if nuclear charge is high. Size of atom. With the increase in the size of atom, the distance between the nucleus and the incoming electron increases and results in lesser attraction. Consequently, the electron affinity value will be decreased. Electronic configuration. The element having stable electronic configuration of half and completely filled valence subshell show very small tendency to accept the additional electron, and thus the electron affinities are low for almost zero in certain cases. Periodic trends. Due to the lack of sufficient data, the changing trends in the electron affinities on moving along the periodic table are less well defined than those for ionization energies. However, it has been observed that the electron affinity in general increases from left to right in a period and decreases from the top to the bottom in a group. These variations are discussed as variation down a group. On moving down a group, the atomic size and the nuclear charge increases. But the effect of increase in the atomic size is more pronounced than that of the nuclear charge, and thus the additional electron feels less attraction by the large atom. Consequently, electron affinity will decrease. This is clear from the decrease of electron affinity in going from chlorine to bromine and to iodine. Variation along a period. On moving across a period, the size of the atom decreases and nuclear charge increases. Both these factors result into greater attraction for the incoming electron. Therefore, electron affinity in general increase in a period from left to right. However, certain irregularities are observed in the general trend. These are mainly due to the stable electronic configuration of certain atoms. There are some important features of electron affinity of element, like halogens have the highest electron affinities. The electron affinity of the halogen are the highest. This is due to the fact that halogens have the general electronic configuration of ns2 and p5 and have only one electron less than the stable noble gas electronic configuration. Thus, they have very strong tendency to accept an additional electron, and their electron affinities are therefore very high. Now, an very important topic, electronegativity. When a covalent bond is formed between two homonuclear atoms, the shared pair of the covalent bond lies exactly midway between the nuclei of the two atoms because both of the atoms may have same attraction for these electrons. For example, in molecules such as H2, Cl2, F2, the electron pair remains exactly at half distance between the two nuclei. However, in the case of covalent bond between dissimilar atoms, the electron pair may be closer to one atom than the other. This is due to the fact that different atoms have different tendency to attract the bonded pair of electron towards itself. The tendency of an atom to attract the shared electron pair in a molecule towards itself is known as electronegativity. Different atoms have different tendency to attract the bonding electron pair towards themselves. Greater the ability of an atom to attract electrons in a bond, larger is the value of its electronegativity. It must be remembered that unlike other atomic properties such as ionization energy and electron affinity, which are related to the individual gaseous atoms, the electron negativity is related to the atoms in their bonded state. There is no direct method to measure the electron negativity. However, various attempts have been made to drive a scale of electronegativity for the elements. Some of these are discussed as first is the Pauling scale of electronegativity. In 1932, Linus Pauling was the first to propose a scale of electronegativity. He proposed the scale based on the bond energy in the heteronuclear bonds. He suggested that if two atoms A and B had the same electronegativity values, the bond energies of the AB bond would be equal to the geometric mean of the bond energies of AA and BB bonds. For example, the bond energy of AB molecule may be written as EAB is equals to the square root of EAA into EBB. This relation is based on the assumption of pure covalence bond in A2 and B2 and AB molecules. However, he observed that for the most of the AB bonds, the actual bond energy is more than the geometric mean of the bond energy of EAA and EBB. This means that two participating atoms have different tendency to attract the shared pair and that have different electron negativities. In other words, the bond AB will no longer be purely covalent. As a result, there is contribution of ionic structure A positive B negative in addition to the pure covalent AB structure. The difference between the actual bond energy of AB and the geometric mean bond energy is known as the excess bond energy and it is denoted by delta E. It is measure of the difference electronegativity of two atoms A and B. So delta E is equals to EAB minus the square root of EAA into EBB. The excess bond energies arises due to the resonance between the structures AB covalent and A positive B negative ionic and is also known as ionic resonance energy. B is more electronegativity than A. By calculating delta E for the different bonds, Pauling suggested the following type of relationship between electronegativity of two atoms XA and XB and the excess bond energy delta E. XA minus XB will be equal to 0.18 into square root of delta E, where delta is excess bond energy in kilocalorie per mole. Mulkey's concept of electron negativity. Mulkey in 1934 suggested that the tendency of an atom to complete for the shared pair of electron in a bond should be the average of the ionization energy and the electron affinity. Thus, according to Mulkey, electron negativity of an atom is equals to IE plus EA means ionization energy plus electron affinity divided by 2. X Pauling is equals to X Mulkey upon 2.8. Disadvantages of Mulkin scale of electronegativity. There are two main disadvantages of this scale. First one is the electron affinity value of only a few elements are known, and second one is ionization energy and the electron affinity values change with the valence state of the elements. The third scale is